I'm Alex Dornberger. I am the president at Cougar Rockets. I am a junior in mechanical engineering. This year we're going to be competing in the 2026 Argonia Cup. The goal for the 2026 Argonia Cup is to design and launch an efficient and optimized two-stage rocket containing any number of golf balls. We're doing that with a rocket called Mega. We also must reach a minimum altitude of 9,000 feet AGL, and we cannot exceed a maximum of 40,000 feet AGL. Both stages of the rocket must be recovered safely and on time in refileable condition.
I am Josh Vandermite. I'm the vice president of Cougar Rockets, and I am a senior level civil engineering student. Our rocket for this year is a 2.1-inch diameter, fully fiberglass rocket featuring minimum diameter on both stages. It will house 15 golf balls and fly to an altitude of around 20,000 feet.
Hi, my name is Wyatt Crane. I'm a student member of Cougar Rockets. I'm a mechanical engineering major. I'm a junior here at SIUE, and I'll be talking about recovery. On our first stage, it'll deploy at booster apogee, and we have one chute, which is a 36 thin mil. And then at our second stage, apogee, which is going to be our max, we have a drogue that'll deploy. And then we'll have about 1,000 feet, we'll have our main chute deploy, which is a 50-inch thin mill. I'm going to be talking about the booster and second stage breakdown. We have a telemetron, which reads our GPS and telemetry data, which is a handband. We have a booster chute charge and a separation charge. We also have an easy main, which is contains a redundant charge in case our first charge doesn't work. Our old one looked like this, but our new one's gonna look more like this, courtesy of Ethan D, which is a student member of Cougar Rockets. And in our second stage, we have this one, which is a Telemega, and it has GPS and telemetry data, also on handband. And we also have a drogue charge, a main charge, and then our sustainer motor igniter. And it also has an easy mini in it, which also contains a redundant charge for the drogue and a redundant charge for the main.
While designing this year's rocket, we noticed that last year's competition was very similar, so we've decided to iterate on last year's design. With that iteration, there are some pretty major changes though. We've decided to go with a minimum diameter sustainer instead of a 38mm motor like last year. Because we've decided to go with that, we will need a new way to couple the sustainer and booster. So this year we have decided to go with an overcoupling. Unfortunately, that's not commercially available, so we are having to go through the process of fiberglass layups for the first time. Another major design change comes with the fact that we'll be carrying 15 golf balls instead of the 10 like last year. So that's going to come with a lengthening of our body tube. During last year's competition, we faced a number of problems. And with this iteration, we're hoping to go back and fix those problems. The first problem came with our app bays being very difficult to prep on the field. So we're taking a step back and redesigning this app bay with more passages for the wires and better ways to connect the charges to the outside of the app bay. Another issue with the wiring that we had is we actually did not pick up our sustainer motor until the day of the launch. So we had no one thought to check that the igniter would actually fit through the nozzle. So that unfortunately required us to actually finish building the motor on the pad, which slowed us down and was ultimately one part in the disqualification last year. Another major problem we faced with last year's competition is the fact that on our sustainer, the main parachute never deployed. While we were at the competition, we had a couple theories of why that was, but we eventually went back, looked at the data, and found out that our shear pin for our main parachute was actually sheared when our drogue was deployed. We think that's because there's just so much extra weight with the golf ball payload that that shock load unfortunately was too much for our shear pin, and it pulled the main parachute out halfway. And while that was tumbling, halfway pulled out, it was flexing our wire, and we can see in the data when we lost continuity for both our main and redundant at about halfway through and then a little bit past halfway through the descent. So our main parachute was unfortunately never deployed. That being said, our sustainer actually ended up completely unharmed, falling from 17,000 feet under just a 12-inch stroke. Our third major problem comes with the fact that we actually had a fin break on our booster. We're not really sure why this happened because we actually recovered the booster and all of the fins were completely, seemingly intact. That booster was then fully recovered, brought back to our vehicles. We drove all the way home, and it wasn't until we were unpacking that the fin seemingly just fell off. So while we think that our fins might be strong enough with the techniques that we used last year, we are strengthening up our fins with a tip-to-tip layup. That's going to be the first time we're doing that this year, so we're learning quite a bit with that.
Hello, I'm Austin Dornberger, the Secretary of Cougar Rockets. I'm a junior mechanical engineering student here at SIUE. I'm going to be discussing the motor selection for this year's competition rocket. For our booster in the rocket, we have a K700, and for our sustainer, we have a K185. We chose this combination because it will give us a good kick off the pad while also maximizing altitude given the parabolic impulse scoring sensitivity. We specifically chose the K185 for the sustainer because it's easy to light, giving us the best chance of having a successful two-stage launch. These motors were the most compatible with our budget while also giving us the highest score possible.
My name is Zach Matthews. I am a first-year mechatronics and robotics engineering student. In order to reduce costs this season and in future seasons of Argonia, we decided to move away from a $50 online purchased flyaway rail that we have been using. We decided to do this because it's pretty expensive and it's broken 50% of the time, and it also is not compatible with 1.5-inch rails. So we are designing a new 3D printed design that uses it's fully custom. In order to reduce costs, we are using the same screws and old rails old like plastic tubing that we have to keep costs low. Current estimates at the cost are around like $8 for a full set.
Staging is one of, if not the most important aspects to safely and reliably operating a two-stage rocket. For our rocket, staging will begin after motor burnout when the telemetrum in the booster fires a separation charge. Then after a fixed time delay, the telemedia and the sustainer will check that the rocket is both going faster than 200 meters per second and at less than 20 degrees of tilt. If this is the case, then the sustainer motor will be fired. If either one of these checks are not met or the sustainer motor doesn't light for a different reason, both stages, the separation charge will still fire and both stages will recover independently. Safe and reliable staging has been one of our main focuses for designing and building our rocket for this year. Last year, we were able to successfully fly a two-stage rocket, so this has allowed us to take on new design challenges, such as building a minimum diameter to minimum diameter rocket.
Hi, I'm Darcy Green. I'm a student here at SIUE. I am the treasurer for Cougar Rockets. I help source the material for the competition and also work on the construction.
My name is Michael Carson. I am a new active member of Cougar Rockets this year. I am a junior mechanical engineering major. and this year I am helping with sanding and general rocket construction.
My name is Ethan D. I am a senior mechanical engineering student here at SIUE, and I have been primarily designing the avionics bays for the rocket.